everybody. My name is Wojciech Zacharczyk and I am coordinator for nuclear energy at the Faculty of Mechanical and Power Engineering. And I have a pleasure to introduce our special guest, President of the Westinghouse Poland, Miroslav Kowalik. Engineer Julia Georgiemans, and Dr. Luca Oriani, who couldn't come due to the pandemic COVID restriction. Our guests represent the Westinghouse, one of the leading company in nuclear energy sector, the company which is seriously considered by the Polish government as a supplier of technology for the first nuclear power plant in Poland. Our guests will provide the lecture about evolution of the light water reactor with, let's say, special emphasis put on the passive safety future. So let me give the floor to the Dean of the faculty, Professor Piotr Schulz, who would like to say a few words. Thank you.
Mr. President, ladies and gentlemen, it's now a known fact that current generation capacity of Polish power plants is not sufficient to meet the ever-growing demand. In the future, our country will have to produce much more energy. We also cannot forget about climate change as well as its negative influence on our planet, the main reason of which are emissions of carbon dioxide. To find a solution to this problem, we keep searching for methods to reduce emissions. This is where investments and financial outlays for building renewable energy sources come from. Energy security is their purpose. Yet, successful transition of renewable sources needs a stable, predictable, as well as emissions-free auxiliary source. We cannot entirely rely on renewable sources because in some cases we could end up without electricity. One of the solutions to this problem is building of nuclear power plants. Modern nuclear energy has everything which is needed to serve climatic purposes. CO2 emissions from nuclear power reactors are so low that they practically do not exist. Unfortunately, construction of power plants has as many supporters as fervent opponents. This is where our responsibility arises, to alter awareness. For many years, the community of the Faculty of Mechanical and Power Engineering, both researchers and teachers, have taken nuclear energy issues very seriously. We want to prepare our students to work in the sector of nuclear energy. Thus, we offer, during master studies in power engineering, a specialty called Nuclear Power Engineering with English as a medium of instruction. Another option is a Polish language specialty, Modern Energy Technologies, where students get to know contemporary constructions of nuclear reactors, analyze nuclear fuel cycle, and acquire safety procedures in nuclear energy. During engineering studies, in power engineering, a course Nuclear Energy is prepared. In mechanical engineering and power machines building, a course Nuclear Reactors is to be taught. The faculty also provides postgraduate studies in nuclear power engineering, which are conducted jointly with the National Center for Nuclear Research. I believe that The lecture you are about to hear will be the beginning of successful cooperation with the Westinghouse Electric Company, as well as of organizing further lecture with other representatives of the nuclear energy sector. I kindly invite to the lecture. Thank you.
Thank you, Mr. Professor. Good morning, everyone. First of all, I'd like to thank the host of this event for organizing the meeting with you, with new generation, talented people we wish to have on the board of Westinghouse. And let me thank you all of you that you are coming together for this lecture. Why we are here? Today's topic is of particular interest to those who see the nuclear energy, nuclear power as a key one shaping tomorrow world. Nobody right now can imagine, life without electricity. So nuclear power is very sustainable source of energy, reliable, and carbon-free, which is really a good feature of this energy. Let me introduce myself, maybe. I should have done this from the beginning. My name is Miroslav Kowalik. I spent over 25 years in the energy sector in Poland, in the region. And 6 months ago, I joined Westinghouse Group, and together with my colleagues from Westinghouse, we are working on Polish nuclear program, supporting this program, which we told you a bit later on in the lecture, in the presentation of Julie. Julie, welcome. She's in present. She's project engineering manager in EMEA. What does it mean, EMEA? It is Europe, Middle East, Africa region, and we have a really the best expert worldwide, probably, Luca Oriani, who is a Senior Vice President for Engineering Service in the Global Chief Engineering Service Office. And he would help us understand the safety, passive safety system of the AP1000 reactor, which Westinghouse offer on the market, as well other features and advantage of the Westinghouse technology. Luca needed to wake up today 5 a.m. because he connected us through the online. Thank you, Luca. So, let me come back to our presentation. I give you a briefing about the Westinghouse. And, but it would be difficult to tell the story in the few minutes, because it is a story about the 130 years of innovation in Westinghouse. You may have heard about the competition between the Edison and Nikola Tesla. And in the early stage of the electricity development as a technology, in the 19th century. At that time, Westinghouse supported Nikola Tesla, as you know probably, because there is a movie which is available on the commercial station describing this story. I really recommend you to watch this film. It's a very interesting one if you didn't make it. First slide, which I like to present, it is about the facts about the Westinghouse statistic figures. We employ 9,000 people worldwide. We are located in the 19 countries, and we comprise of the 5 businesses. From the new build lines, which we be representing, me and Julie, to the service business line, which help operating the current reactors, which producing the electricity. Probably you know how big nuclear energy is in the worldwide. Maybe just to give you a certain facts. 10% of the worldwide electricity has been produced by the current reactors. Half of them is under the Westinghouse technology. Do you know how many reactors right now working worldwide? Maybe one kind of a guess. 440. So what else? We have 70 facilities, and our technology generates nearly 50% of the world's nuclear power, which means that it is composed of the 10% of worldwide consumption. Why we are here? This slide shows Westinghouse commitment to Poland, to Polish nuclear program development. And we are working under the intergovernmental agreement signed this year in February. And under this agreement, we are preparing front-end engineering design study. Probably somebody of you learn this word. However, we are more familiar with the feasibility study. What is the fit-end engineering design? It's comprised of some basic concept design, project schedule, estimations of the cost, mapping of risk, licensing approach, etc. Why is so important that the Westinghouse is committed to the Polish nuclear program? Because Poland is in the critical moment right now, in terms of the future energy mix, because of some big trends which already happens, Green Deals, climate challenges, climate change, which we believe, we can create a more friendly environment for the new generation. So, and we believe that Poland needs proven and safety technology that helps Poland to achieve climate goals, meaning neutral climate by 2050. The IP1000 reactor is as such which really suits to the Polish needs, we believe. It is also worth mentioning that the potential of the Polish industry is huge. Westinghouse business model is very designed to cooperate with the key local subcontractors. We already had the meeting with the Polish suppliers 2 months ago, and we are in the close relation with them to help how to proceed and how to increase the capability, mainly in the quality processes, just to be part of the nuclear business. We are here also just to present you our best product, the features, because we believe that it brings a prospects to you and maybe to your career, and you decided just to be part of this sector. About the footprint, how the Westinghouse is structured worldwide. As you will see, this is the international global organization located on each continent. We are very strong in Americas, in Europe, in Asia, and partially in Africa, where our reactor is working. Because our businesses are dedicated just to help the customer in the daily operation of the reactors, as well, we hope to build the new fleet, as it is a case in Poland. And what else is worth mentioning? That for the Westinghouse, Europe market seems to be very important in the coming months, in the coming years, because of the good perspective. Also, it creates a perspective for you. You know, just after graduation of your study, you may find this sector quite attractive, you know, and good for your future, building your good and sustainable future. We want to benefiting also for the huge human potential and talented people in Poland. In August, we opened the Global Shared Service Center in Krakow. Probably you've heard about it. And we created over 130 high-skill jobs in Krakow. In the beginning, in the center, staff will support Westinghouse Group in the area of finance, HR, and supply chain. At the later stage, we will plan to add R&D as well, digital innovation. So that's the perspective, and it's our belief and commitment to the Polish market and the regional market. Why region? Because you will see there are plenty of opportunities in new build. Because Julie may explain you a bit more about our competences in the service field, where we provide to the current customer operating reactors. But here you will see the new build, you know, is big potential from the point of view, from the economic point of view, as well from the point of view of the gaining and leveraging of technical knowledge for the given industry, also for the Polish industry. That's my message, which I like to pass to you today. So, as you see, there is a big cake, and probably it creates a good opportunity for the sector, civil nuclear sector stakeholders. So before I move on to Julie, I'd like to recap. Westinghouse is strongly interested in developing Poland's nuclear program and demonstrate full commitment to Poland, wants to bring technology excellence, and is open for broader cooperation with academias like yours, academia, with suppliers and other stakeholders. Why others are talking about it, we have established Polish subsidiary of Westinghouse, is a fact. It is not an office, but subsidiary, you know, the legal entity which operated since August, with over 130 people on board. So, again, I wish you a fruitful lecture, and the floor is yours, Julie.
So I will actually let Luca introduce the technical side of the session.
So good morning, and thanks for having me. I'm Luca Oriani. I'm the Chief Engineering Services Officer for Westinghouse. I'm responsible for all of Westinghouse plant and component engineering resources, over 1,300 engineers globally, with over 40% of our engineers that are actually in the European region. I apologize for not being able to be with you. Unfortunately, some of the travel restriction changes that occurred last week made it impossible for me to travel and be able to be back in the United States on a sufficiently quick schedule. So, but Julie will do an excellent job, like she always does, in terms of introducing the technical topics. What Julie is going to go over through this discussion is she's going to discuss the early development of the light water reactor technology with a view on the United States, which is where the technology originated and how it was deployed throughout the world. She will then discuss specifically for pressurized water reactors the key systems, and then discuss how the evolution of the technology developed with the culmination of the transition from the first and second generation active plants to the passive AP1000 technology, and a discussion of what are the key advantages and the key benefit, especially for operations in a modern grid with a high content of renewable. So Julie, if you can go to the next one, I think I'll just pass it to you. You can go through the overview, and then I'll pick it back up to give you an introduction when we get to the AP1000. Julie?
Thanks, Luca. Okay, so we'll start our story about what happened at the CP1 reactor in 1943. That reactor is the first reactor where sustained criticality was actually observed. What it opened as a door is another application of the atom. Well, before, there was obviously lots of research being done in terms of military applications. This one opened the door for power being produced by the atom. Because on that day, that reactor, we were able to sustain a chain reaction, safely controlling it, and basically opening the door for many different applications. That led to the United States Congress to establish the Atomic Energy Commission, which is actually the ancestor of the US regulator today, the Nuclear Regulatory Commission. And that happened in 1946. After that, there were lots of investigations in universities like yours about different concepts, looking at different ways of cooling the reactors, different ways of moderating, and we will see in a bit what it means. And that led to the identification of 5 different concepts that looked very promising in terms of producing power. So when we talk about producing power, it may mean producing electricity, as is what we are doing with our AP1000 reactors, and hopefully we'll be doing in Poland very soon. But it may also mean propulsion means. And actually, the US Navy recognized very early on the potential of nuclear power to provide that motive forces for them. And one of the reasons is because nuclear energy is extremely compact. So you can provide a lot of energy with a very small reactor, which obviously when you need to move it in a submarine is a very attractive benefit. However, they have other requirements than what you may have on a reactor that is there to produce power. So space is a constraint, but also how much a protection you're providing to the personnel who's going to be very close to it. So that led to another program in parallel to the previous one that I was mentioning, into exploring of concepts for power reactors, into looking specifically into means of propulsion for submarines. That program, that Navy program, actually led to the first pressurized water reactor designed by Westinghouse, which was the Mark I prototype reactors. That prototype reactor was on land. It was to demonstrate the technology, but shortly thereafter, its big brother, Mark II, was actually embarked on the Nautilus submarine, which started navigating in 1955. Again, we have 2 ongoing efforts in parallel, obviously feeding each other, but you have the nuclear power and the nuclear submarine one. But another thing that's going to change in the early 50s in the US, we have a change in president. And there is a realization by the new US president that atomic energy could also be used as a diplomatic means. Engaging different countries throughout the world, sharing that knowledge in exchange to asking for limiting the development of nuclear weapons. And that's what we call the Atom for Peace. First speech that he made at the United Nations and then effort. So Well, before 1953, all nuclear research in the US was classified, which means that only US approved people could get access to it. In 1953, it opens the door for actual commercial operations of nuclear power reactors, as well as export of that technology into other countries. The Atomic Energy Commission, their mission changes slightly to be more what a regulator is today. So they will be encouraging the use of nuclear power, but also overseeing and regulating the safety of the installations. That leads to the first nuclear power plant, so the first plant which is dedicated to power production, only designed and built for that. And that happened in Shippingport, which is actually not far from our headquarters in the US. That achieved first criticality in 1957. So that's just an example of a nuclear program, how it happened, how it was the very start of how nuclear power plants were developed. But from there were lots of companies in the US who had participated to those programs and started selecting one of the concepts that had been pursued as part of the national program to offer it commercially to utilities. So Westinghouse Electric Company, but two other American companies decided to go for the pressurized water reactor design. General Electric, that you may have heard of, they chose to go for the boiling water reactor concept. So both operate with light water reactors. What we call light water is normal water, if you want. The difference is, how do you produce steam? In a pressurized water reactor, you maintain your primary circuits, the one that cools the reactor under pressure so that it doesn't steam, and you use a heat exchanger called the steam generators to provide, to transfer the heat from the primary to the secondary circuits, and that's the steam that's going to go to the turbine. Well, in a boiling water reactor, the steam is directly produced in the reactor to go to a turbine. National laboratories, universities, research centers in the US, while those commercial reactors were being deployed, continued working on advanced reactors and other concepts. So often when you talk to people like us that come from a technology supplier in the industry, we talk about generation of plants. And just a word so that you understand a bit better some of the things I will talk about after. What we talk about the generation one is exactly like Shippingport. Those were the very first unit of their kinds that were brought almost as a demonstration of the capability to produce electricity with nuclear power. Generation 2 is more the commercial fleet, what is operating today, which has been developed based on those prototypes and the lessons learned from those initial reactors. Generation 3, it was being built, has been built very recently. The big difference between a Generation 3 and a Generation 2 is how they have incorporated lessons learned about particularly the core melt accidents, including mitigation features for core melt. But then within Generation 3, we have different kinds of plants. You have those who are just building on what Generation 2 did and added a few more systems for that, severe accident mitigations, but also added diversity. And then you have Generation 3 Plus, as we call it, is where we took a different approach on safety. So those are all the passive designs, and this is what we will talk about in the second part of the presentation. Let's not forget about Generation 4. Generation 4 has been worked on for quite some time. It's a number of concepts that requires a lot more research and development to be ready for deployment, but that provides additional benefits than light water reactors. For example, they can operate at higher temperatures, which opens the door to other applications than electricity production. But they could also use what we call closing the fuel cycle, which means reusing some of the fuel waste from other reactors as a fuel for themselves. This is the example of the United States. Obviously, other nations, particularly those who were already active in atomic research, also had similar program. The United Kingdom developed their own designs, the Magnox reactor, as we call them, and the advanced gas-cooled reactors, which are still in operation today. The Canadian went with heavy water reactors, so it's a reactor which uses deuterium instead of light water. The CANDU, which is in operation in Canada and in a few other countries. And Russia, of course, also developed their own designs as part of their nuclear national program. All the companies that today develop nuclear reactors, they either stem from those big national programs, so like us, like Rosatom, for example, for Russia, or they were developed through technology transfer. So those initial countries that developed concept had transfer agreement, transferring the technology to third countries, to third-party countries, and then those third-party countries developed their own industry around it. Key systems and components. The purpose of these sections is just to introduce some of the concepts in a nuclear power plant so that it makes it easier to understand what we're going to say about AP1000. So I'm going to try to go relatively quickly so that we can focus our time on AP1000. So as I was mentioning when I mentioned pressurized water reactor versus boiling water reactor, in a pressurized water reactor, by definition, what we are trying to do is maintain the primary loop, which is in red in this picture, under pressure, very high pressure, 155 bars, so that the water doesn't boil. This is one of the things that we are really trying to do. So we have few components which are there to do this, and I will mention them in a second, but basically this is a loop circulating water through the core where it gets heated up by the nuclear chain reaction, and we will come back to that. And then that heat is transferred to a secondary system through the steam generators. That secondary system operates at a lower pressure so that there it will actually evaporate when the heat is transferred, and that's the steam which is produced by that heat transfer which will activate the turbine. And in the condenser, what's coming out of the turbine is being cooled and residual heat is being transferred to the environment. So we have three systems, three layers, basically, in the plant. And this is important because that's one of the advantages of pressurized water reactors, the number of barriers they provide against the dispersion of radioactivity to the environment. So fuel is encapsulated into so fuel elements come from pellets. So there's very small cylinders, if you want, of oxide uranium. They're stacked into a fuel rod. Fuel rod has a cladding. That cladding is made to resist the pressure that will be building up as we operate the reactor. Rods are being arranged in what we call fuel assemblies. So you put lots of rods next to each other in a squared array, and this represents the form under which you're going to move fuel in the plant. And then obviously we place a number of fuel assemblies inside the reactor. Nuclear energy is very, very compact, as I was mentioning to you earlier. We replace about 40 tons of uranium in a reactor. That represents what we need to change every 18 months, pretty much. Well, for example, a coal plant burns 10,000 tons a day. So you can see the difference in terms of fuel. So we rely on fission chain reaction to produce the power. So we have a neutron who enters in collision with uranium-235. That's the one uranium isotope, which is fissile. It then splits into different sub-elements, but it also releases 2 to 3 neutrons. Those neutrons need to be moderated. And what that means is that when they are born from the fission reaction, they are extremely energetic. They have lots of kinetic energy. And we need them to slow down, to lose some of that kinetic energy so that they enter a range of energy where they can be captured by the next uranium-235 atom. So what we're going to do is we're going to use water both as a coolant and as a moderator, as the means to cool down, to slow down the neutron. The neutron is going to enter in collision with the atoms with the molecules of water, and for each of the shocks, it's going to lose some of its energy. So how do we control the chain reaction? Well, first of all, by acting on the moderation. When the temperature of the water increases, that means the density of the water decreases, so you have less dense water, which means that the neutron will enter into less collisions. So you lose moderation, which means you decrease reactivity of your reactor. And this is one of the good features of a pressurized water reactor, also in terms of safety, because it gives you kind of a natural negative feedback. If something goes wrong and temperature increases inside your reactor while you don't want it, actually it will automatically create a decrease in the reactivity. But we also have designated, designed for means to control reactivity. We have the control rods. Those are huge absorbers of neutrons that we can enter into the fuel assemblies. If we have an emergency, those rods will automatically drop in the reactor and shut it down, the reaction. But we can also use chemical ways of doing it by dissolving some elements like boron that will actually absorb neutron as well. In the primary circuits, we have a number of elements. So the steam generators, as I mentioned, those are the big heat exchangers. It's important for those of you who didn't have the chance yet to walk into a nuclear power plant to notice the size of those things. We're talking about a 20-meter tall heat exchanger, so this is quite a beast, if you want. But really, the primary circuits flows through the tubes. Those tubes, the tube bundle is being flooded in water, and that water will boil off through the heat exchange. We have reactor coolant pumps. We need lots of water to ensure we can remove the heat from the reactor properly. So those are also big beasts that will ensure enough force flow through the core to maintain it at the correct temperatures. And one of the features they also have in a nuclear reactor is what we call a flywheel. And a flywheel is basically only like a big weight that we have on top of the pump. You are going to ask, why are we paying the cost of making that big weight turn with the pump during normal operation? And it's actually for, in case of an emergency, if we lose any power to the pump, that means the pump won't slow immediately. It will actually have some inertia. And so that will ensure that some flows continues through the core at the very beginning of the event, and that protects our fuel. And finally, we have the pressurizer. That is the equipment which is used to ensure that the primary circuit remains pressurized so that it remains liquid. The primary systems operates around 300 Celsius degrees, so you realize, we need lots of pressure to ensure that it remains this way. So this is basically a big tank with water and steam, and the steam create the pressurization of the circuits. The most important element is the reactor pressure vessel. This is where the core will be located. This is where all the elements, the control rods will be manipulated, and all the structural support for the core and for the control rods will be provided. Key systems. First thing that we need to do is control the reactivity. Obviously, we can do it with the control rods that I mentioned, and it will shut down the reactor when the reactor is hot. But as we cool down the reactor, and that's one of the things we want to do when we have an accident, we will basically increase the reactivity of the core. So we also need to provide borated water to the reactor. We also have accidents when we have leakage or even breaks in the primary system. And one of the things we really want to do is keep our fuel or core covered in water so that there is always a way to remove heat from the nuclear fuel. So we provide a number of systems in the plant to provide either just what we call the high-head safety injection, so borated water at high pressure for events where the reactor system is intact, there is no breaks, or even further sources of water for when we have a break in the systems and we want to ensure that we keep a certain level in the reactor. So because we need to inject from 150 bar to basically 10 bars, we need to have different pumps because one pump is it's difficult to design a pump to operate over such a large range of pressure. So that's why we have what we call high head and low head pumps. We have redundancy, of course, on the systems, and we also have a lot of support systems that are being required. We need to provide electricity to power those pumps reliably, so that means with backups on site. We need to provide the instrumentation and controls, which will ensure that the pump is delivering the amount of water that it needs. We need ventilation systems to remove heat from where the pump is located, because obviously the pump will create lots of local heat, and we need to remove that heat to ensure it can operate for extended periods of time. This is very important because that's one of the reasons why we went passive. So remember, it's not just the few pumps you see on that picture, but it's the entire network of support systems that is required. Emergency feed water. So in the steam generator, the big heat exchanger that is used to exchange heat from the primary to the secondary, we obviously, as we are producing steam continuously, we need to provide water continuously. And we have what we call the main feed water system. That's the normal alimentation, feeding of the steam generator in order to ensure that our tube bundles remains covered. But if we have an event, one of the first things we try to do is actually bring what we call emergency feed water. So that's a backup to the main system in case we lose the main system to provide cooling through the steam generators. So one of the important barriers to the release of radioactivity to the environment in case of an accident is what we call the containment. So that's a structure which basically surrounds the primary circuits and some its ancillary system. And that's the one we're gonna rely on to limit how much is being released to the environment and to the surrounding people in case of an accident. So it's important to protect it. It's designed to accept a certain peak pressure because if you have an event where you're suddenly releasing a lot of steam or a lot of water inside that building, you will have a peak pressure, but it's important to keep then cooling the building and ensuring that heat is being removed. So we have a number of systems which are taking care of this, again, relying on pumps, relying on heat exchangers and a number of tanks outside containment to do the job. So we already mentioned in the introduction that AP1000 and actually passive technology is different. And it's not a conclusion, it's not a direction we suddenly decided one morning, okay, let's go different. Actually, it's a result of things that were happening in the US industry at the time. In the 1980s, in the US, we actually kind of are at a stop in terms of how many plants we were building. We had built a lot of units in the 60s and 70s, but in the 80s, the focus kind of turns into how can I get more electricity of what I have already built? Can I increase the power level at which I operate? Can I limit how often the plant needs to be taken down for maintenance or for unplanned issue? And so there was a lot of efforts done on how much do I produce with my existing units and very little going on in terms of new construction. And part of the reason was actually the trends were quite bad if you looked at it for utility. We were taking longer and longer to build a nuclear power plant, and that's because as time was going by, we had more and more requirements coming from regulators and coming from utilities. Those requirements were funded. They were not bad requirements, but the only way we were addressing them was by adding complexity to the plant, adding layers of equipment, instead of trying to redo the thinking and thinking about how we could do it in a more efficient way. So just this is the average construction time. As you can see, it was continuously increasing. We were also building larger units, which means obviously we needed less to produce the same amount of power. But one thing I wanted to show to you is also how US was different from what was happening in the other large nuclear nations. US actually stopped building in the 80s, while all the other countries like France, like Russia, big nuclear countries, actually were continuing building. So they didn't have that pause, that break that we had. But it's really that break that made us take the time to do things differently. And it's a push that didn't come from technology developers only. It's actually really an industry push to realize we need a product which is a lot more standard. So we need to understand the requirements in advance and design for those requirements. And this means we need two things. We need utilities, customers that will operate the plants, to get together and tell us in one single place, this is all we want, all together, we agreed this is the standard product we want, which means that to customer A, B, C, D, I can sell the same plant. I don't need to redo the work all the time. But we also need the regulator to tell us in advance, okay, your plant design is acceptable. It does meet the requirements. It does a good job in terms of addressing potential issues. Go ahead, no, anyone who wants to build that reactor can do so because we've already approved it. And so while the utilities worked on a common set of requirements, the regulators also developed a way for vendors like us to come and offer our design for review before it is even started on a project with an actual customer. And this is, I think, really where the difference in approach stem from those who decided to build upon what Generation 2 reactors looked like and address the few new requirements, the new requirements being addressing core melt, and also addressing further diversity / multiple failure type of scenarios. And others, not just Westinghouse, but most American companies actually, deciding to look into how can we do it differently so that we can achieve the same level of safety, but we do it with simplification. And simplification is really the key. How can we be simpler and yet safer than the previous generation of units? Because that's the only way we can be affordable, and we need to be affordable in order to have customers, basically. So Luca, you want to introduce AP1000?
Yep. So I think Julius went through an overview of nuclear power plants and specifically light water reactor. Now we're going to move a little bit to discussing the AP1000 and its technology. And you'll hear Julie keep repeating certain keywords: safe, simple, and standard, which are the fundamental principles that every Westinghouse engineer, and for those of you that will join us in the internship next year, you'll see that those are the principles that are inculcated to AP1000 and Westinghouse engineers since they actually start working. So as we go through the AP1000 started thanks to that period in US history where there was already a very large park of nuclear power plants, and for a number of reasons, it was more efficient as we assimilated the lessons learned from some of the early stages of deployment, as well as some specific accident that occurred in history, in which we were focused in the United States more on improving the availability of the existing station. To give you an idea, while no plant has entered operation after the started construction until we started the AP1000s in the 2010 timeframe, after 1980, the power production from nuclear in the United States has increased by almost 30%, which is the equivalent of 25 to 30 new plants. Now, thanks to that period, we started looking at some of the issues associated with the previous generation of nuclear plants. And the first aspect that we looked at was the conundrum that increasing safety led to continuously increasing and escalating cost. And that was due to the fact that we were just adding more and more of the same systems. That's a concept that is called redundancy. For the AP1000, we wanted to break that paradigm and be able to develop plants that would be safer while at the same time being cheaper. To do that, we had to switch from the concept of just redundancy to a mixed concept of redundancy and diversity. Passive technology, so the reliance on natural processes, was the fundamental at the fundamental basis of that change. The passive design allows us to need less equipment to perform the same functions and achieve an even better safety level, which allowed us to compact the footprint of the plant, which allows us to reduce the construction time, construction quantities, and the cost of building the plant. Then we wanted to have a plant that was pre-licensed. We wanted to have a plant that was not only simple, but was standard, which means we work with the regulatory agencies in the United States to start the licensing process of the plant while it was still being designed. The AP1000 is the most licensed plant in the world. Not only it has a license from the US Nuclear Regulatory Commission, but it has a license in China, it has the generic design approval of the United Kingdom, and it went through a number of different reviews with both the IAEA, WENRA, as well as the European Utility Requirements Group and the US Utility Requirement Document Group. As you keep that train of thought, so you want a plant that is safe and simple, you want it standardized so that the licensing process can be standardized, but you also want standardized so that you ensure you have a complete detailed design before construction starts. For example, for the units we are currently discussing for Poland, the detailed design of the plant with very limited exceptions is already completed, and the remaining element will be completed about a year before we even start nuclear construction. For the large structural modules that Julie will introduce that constitute the majority of the building, the design for these new plants in Poland and Eastern Europe is already released to supplier to actually perform the detailed fabrication planning. The next step, the next box you see there is interesting because it talks about a horizontally diversified global supply chain. So this comes to a difference between Westinghouse and a number of other vendors. Westinghouse is structured not as a national US company, but as a global international company. If you wish, Westinghouse in nuclear is born directly straight out of the Atoms for Peace initiative that the Eisenhower administration in the United States initiated in the 1960s. The key difference from other vendors is that we tend to source as much as we can of each project locally. Our engineers are hired in the countries where we have plants. If you look at the map of Westinghouse engineering resources, every country where we have a plant, we have engineers. And that's because we source our talent close to where the plant is. Additionally, we structure our projects such that we maximize the amount of content that we can buy from local supplier rather than having to transport it from the country of origin. Modern technology also allowed us for the AP1000 to develop state-of-the-art digital engineering methods and a 4D integrated construction model. One of the challenges we identified, of course, as we optimize the design and we go for this compact plant, it's very inefficient to design these plants like the majority of power plants are designed in the world, which is essentially based on drawings. We designed the plant entirely in a 3D environment, and our building information management system which is integrated with our plant life cycle management system, is the state of the art not only for the nuclear industry, but also when we benchmark with the power industry at large. Julie will talk about modular construction. Why are modules so important to the construction of the AP1000 and why they are so instrumental in maximizing the compactness of the design. Let's go to the next one, but keep in mind those three words: safe, simple, standard. And that's where we're going to spend the rest of the discussion. Now, Julie will discuss the plant. I'll just spend a few minutes to introduce the heart of the plant. If you wish, that picture that you see there is what we call the reactor coolant system. That's where the reactor is housed in that vessel right there at the middle of that picture. Now, when you look at the scale of the plant, it's quite intriguing how small of a percentage of the plant is actually the vessel where the nuclear reaction occurs. That vessel is the only place in the plant where a nuclear reaction occurs. Everything else is just a regular plant. It's designed to do nothing else than transfer heat from one place, the reactor, to the turbine to generate electricity. The fuel, the reactor vessel, and the internals of that reactor vessel are based on 60 years of Westinghouse technology. The key difference is we apply the lessons learned from decades of operation so that the vessel is designed to begin with for a year of at least 60 years, and and the amount of design margins that are included will allow the AP1000 units to extend that to 80, 100, and potentially 120 years once they are in operations. Steam generators that I think Julie referred to as a beast, they are the Delta 125 model that Westinghouse has successfully developed and deployed in both Korea and the United States prior to using them in the AP1000. Reactor coolant pump is one of the innovations of the AP1000. This used the CAN motor technology such that the motor of the pump and the pump is completely encapsulated. That simplifies a lot the auxiliary system for the plants, reduces maintenance, and it's a development that came directly from the US Navy in terms of their an adaptation of the propulsion systems used by the United States Navy submarines specifically. We talked about the simplified loop and the larger pressurizer, which I'll explain why it's so important to the way the plant operates. That large pressurizer is one of the reasons why the AP1000 specifically is designed to work in a more integrated grid with renewable. So when you look at operational excellence, the AP1000 has some characteristics that have been extremely effective in the operations of our early units. Specifically, if you wish, is a plant that is specifically designed to work in a grid that has a high content of the renewable. The previous generation nuclear power plants were mostly designed to operate in what is called base load. That was essentially adapted and optimized for a grid in which you had nuclear and coal plants for what is called base load power generation. Essentially, you run them at 100% of the time as long as you can. And then typically gas or oil plants were used to actually provide peak power, so to adapt the generation of power to the specific time in the day. Now, a modern grid that tends to introduce more and more renewable, but a grid that has a high content of renewable presents some significant challenges because renewable tends to produce electricity at a somewhat partially predictable, but also with some significant unpredictability, but also with a very cyclic approach in which the power generated is not a constant during the day. If you try to build a grid that incorporates a high level of renewable, while you don't have nuclear power plants, you actually can get to the paradox of actually increasing your carbon emissions because you are going to have to heavily rely on gas and oil plants to modulate the power generated during the day. That's some of the challenges that some countries like Germany are facing right now. Now, units like the AP1000 are specifically designed, as you see, to allow a capability for fast power maneuvers on a nuclear power plant. And they have three characteristics that were specifically included in the design to enable that. The first one is the use of what we call gray rod. So instead of actually only be able to control power by changing the concentration of boron in the water, we actually, which of course is low and requires time, we actually change the power level of the reactor by moving a specific set of control rods in and out of the reactor core to modulate its power. The passive system allows us a very large amount of margin between the point where the plant operates and the point where the safety system take over control of the plant from the operator. As such, they allow us for an ideal design of our digital control system that not only are more efficient because they replace the old analog design that was used in previous generation of nuclear power plants, but they also have a significant amount of margin between operation and the safety limits of the plant to actually control the plant operation. And the large pressurizer, if you wish, just imagine it like the shock absorber in your car. It's literally designed so that as you hit bumps, power changes, it modulates and absorbs and reduces the impact of those on the operation of the reactor. I think, Julie, I'm going to pass it back to you as you go through some of the design features on how are these characteristics achieved.
Yeah, so we mentioned already a few times that one of the areas where we achieved a significant simplification is how do we deliver the safety functions? How do we control the plant in case of an emergency? So the next few slides are about trying to illustrate some of those simplifications to you. So what do we mean by passive safety systems? Those are systems that are on standby during normal operation. They do require a one-time valve alignment in order to actuate. So, for example, it will be, well, actually I will have a few examples after, but what we certainly do not want is have any kind of rotative equipment in their design. We don't want pumps, we don't want fans, we don't want anything that needs to be controlled. We don't want to have to close valves again after they were open. We want one time, either make it open, make it close, and that's the only thing we need. Because of this, the only thing we require is for a very short period of time, some power available to move the valve, as well as the INC systems to send the signal. But other than this, no ventilation, no power systems for extended periods of times, no AC power at all, and also no operator action. We want everything that requires to happen to be done from the plant protection system automatically. That doesn't mean we got rid of all the good things we had in previous designs, but those systems, we kept those that supported normal operation and could also play a role in emergencies in case of accidents. We optimized their design for normal operation while providing a level of assurance that they will be there in case of an emergency by providing redundancy where it makes sense on a technical point of view. But in any case, if we have an accident, we don't need those active systems. They are only providing a first line of defense in case of an emergency. So, passive processes. When we say passive systems that only relies on passive processes, we think about natural circulation, gravity, evaporation, and I will just show you a few examples of what it can do and how it works. I mentioned at the beginning that one of the functions we need to fulfill in a nuclear power plant is provided highly borated water in case of an emergency. In a conventional active pressurized water reactor, we have a number of pumps that are required to deliver that function. In AP1000, we actually have a tank, well, two tanks called core makeup tanks. They're the tanks in blue in this picture. And we're going to drain them through natural circulation. they have an inlet line which is connected to the primary loop, and that inlet line is insulated, firmly insulated. So basically it remains hot because the primary system is hot and it's connected to the primary systems. And it's insulated from its environment so that it doesn't dissipate the heat that is inside. That's why in the picture, it's actually being designed in red. The outlet line, what comes at the bottom of the tank and goes to a dedicated line for injection into the reactor pressure vessel, is not firmly insulated. So any heat contained in there will actually be dissipated into the containment building. Because of that, it's much colder than in the inlet line. The core makeup tanks are isolated by one valve, normally closed when we are operating. In case of an emergency, if we have an excursion in parameters that trips the reactor automatically, the plant protection system will also activate those valves to open. We only need one of them to open. We have two only for the purpose of redundancy, so that if one fails, we still have the other one to open. Once that valve is open, what you're gonna have is a hot column of water at the inlet of the core makeup tank and a cold column of water at the outlet of the core makeup tank. Because cold water is heavier than hot water, it will actually naturally induce the circulation of that, what is contained in that tank, and provide highly barorated water into the reactor system. So on standby, nothing moves until those valves are open. As soon as those valves are open, that tank is basically being circulated and mixed into the reactor coolant system. Another example of a passive safety systems is the accumulator. The accumulator is another source of injection, so it's also highly barorated water. We only need it if we're losing inventory from the reactor coolant system, so if we have a break in the system. And it's basically a tank with a nitrogen gas cover, so it's being maintained at a certain pressure and only isolated by a check valve. And a check valve is a valve that will open as soon as the pressure on the back end of the valve is lower than the pressure on the upper side of the valve. So we pressurize that tank so that as soon as the pressure in the reactor coolant system drops below a certain set points, the value of the pressurization, it will basically inject. And the beauty of this system, it's already in the existing units, at the operating units. It's actually, we always had some passive safety features in operating pressurized water reactor. We only took that concept and went further. To remove heat from the reactor coolant system, so decay heat as well as stored heat, we also use a dedicated heat exchanger, which is located inside containment. And it's basically based on the same design as the core makeup tank in terms of how we're gonna ensure that we have flow through that heat exchanger. We again gonna have an inlet line connected to the reactor coolant system and firmly insulated, so staying hot, while the outlet line is actually non-insulated and so will dissipate any heat, so being cold. Once the isolation valves open, it will flow and create a natural circulation through the heat exchanger. The heat exchanger is just a very large number of tubes located in a huge pool of water. As hot water flows through the tubes, heat is being transferred to that tank. That tank will heat up slowly. Eventually it will boil off, and we will see in a minute what we do with that steam. We don't want AC power, but actually in AP1000 we went even one step further. One of the things that we did is that all the safety features we would require to mitigate a loss of power event, because that is the strange thing with a nuclear power plant, is that when we lose power, we actually need power to remove decay heat, which is power. So in operating plants, we have a number of power systems that are there as backup to the backup, backup to the backup to the backup, in order to provide that power which is necessary to activate all the pumps that are required to circulate. In AP1000, initially, like all our passive safety systems, what we need is a one-time valve movement. And we actually designed those valves so that they will automatically open even if we lose all power at the plant. So we actually designed the valves, so we need power to maintain them closed. And you can do that with solenoid valves and things like this to achieve that result. So you can design your valves so you require power to maintain them closed, which means that if you lose power, they switch to the open position and your safety systems activate. Another example of a passive features on how we can achieve the same functions as before, but with simpler systems, is removing heat from containment. Traditionally, containments are usually a concrete structure with a steel liner. There has been containment vessels which are only metal in the past, and we actually chose to use that option because then we end up with a huge heat exchange surface. Metal is extremely good at conducting heat. We all agree, I think, as engineers. So what we're going to do is we're going to use the heat exchange, the containment vessel area, the surface of it, in order to remove heat from inside containment. So we're simply going to pour water on top of it. That water is going to flow down the sides of the containment vessel. It will evaporate, and that will remove heat from inside containment. It's really simple. And we only make the tank big enough so that it is enough for 3 days of pouring water on top of containment. So inside containment, everything is taken care of. We actually isolate containment when we are in passive safety mitigation of our units, and we use our passive containment cooling systems to remove the heat from inside containment. And this is the type of advantages that passive safety really brings, and particularly in a post-Fukushima outlook. So first of all, AP1000 was designed so that all those systems that I just mentioned and that are required to mitigate most of the events will actually automatically actuate if we lose all power. They are self-sufficient. They do not require any other support systems. Because they will anyway actuate, we don't even need an instrumentation and control system to realize something is wrong, because when we lose the power, it will actuate. They don't need any support systems. After 3 days, we do need to take some actions to extend the operations, but 3 days is a very long time in order to have the possibility to connect what needs to be connected. And finally, because everything is inside containment, that containment is a very thick metallic vessel. It is protected by the shield building, which is a very thick concrete building, literally designed to take on an aircraft crash. That's why we call it shield building. It's because it's shielding the containment vessel. So when you think about the type of external hazards that created the catastrophic situation at Fukushima and the loss of infrastructure, obviously for us it will not affect those systems that I was just mentioning because they are protected by those structures. Now, everything I said is that it was great, that it was beautiful, simple, that it worked perfectly, and that you didn't need anything. But obviously, there are some things that are different when you do passive safety, and one of the challenges is how do you demonstrate them? How do you ensure, since they're new, since they're innovative, how do you ensure you can demonstrate not only that it works on paper, but that it also works at your plant? So you have two steps in that demonstration. The first one is what we call the safety analysis side. So we first need to demonstrate we have the tools, we have the computer codes that are sufficiently supported by testing in order and validated by that testing to predict how passive safety systems will work in the plant. But after that, every time we build an AP1000, we also need to demonstrate that what we have built corresponds to what we have assumed in our safety analysis. So there are two steps to the demonstration for each AP1000 unit, that it will operate as we have intended so when we designed them. The good thing about passive safety system is that not everything is new, and I think this is one of the key things. We had natural circulation as part of the safety phenomena in existing previously operating units. We have some passive features like the accumulators that were already existing. So we identified where were the areas where we were lacking information, and we carried out significant testing. Sometimes testing was to address a very specific aspects of passive safety systems, like defining the heat transfer correlation from a heat exchanger in natural circulation. That's a very specific aspect. Looking at how different channels would influence each other in a multi-channel natural circulation heat exchangers. That's another example. But also, how are they going to work all together? Like, we had some test loop that were looking at the integrated response of the passive safety systems for AP1000. And the picture you have on the right is an example of such facility in Italy, where for us the most important parameter is actually the height of our test facility, because height is what drives a lot of the natural circulation flows and so on. Volume of the test facility is not as important, but other than the volumes, the diameters of the tanks, it was basically a full height test loop where we could do simulations of many accidents. So that testing allowed us to develop our passive safety systems, firm up our design, then allowed us to adapt our analysis tools that we were using for active safety plans in order to be able to do what we called accident analysis. And we look at different accident scenarios. Some of them are a single failure, some of them are multiple failure. I don't know if you're there yet in your study, so I'm going to stop there, but we look at many different types of sequences in terms of what can go wrong in a nuclear power plant. We also look with our high fidelity simulator about how the passive safety systems will work with operators. I mentioned before that we have no operator action required. But obviously, we don't expect the person which is in the control room having the worst day of their life because they have an accident at the plant to not do anything. We just don't require them to do anything. So we don't credit any actions that they may take. But we still want them to ensure that if they do take actions, if they are available, that those actions are not negatively impacting our passive safety systems. And that is what we do in the design stage. After that, once we are building an AP1000 unit, we also need to verify the specific safety systems we built in that unit to ensure they do meet the assumptions we made in those analyses. And so we have a starter program, extensive starter program, to verify the performance of the safety systems as they were built. And yes, it can be tested. You can measure how much heat is being transferred to that tank, for example, inside containment. You can measure what's the flow rate in natural circulation for some of those natural circulation loops. All this is measurable. So we can start up, during the startup program, the initial final verification before we start up the reactor. We can verify the performance of those systems, and we can, of course, continue doing so through the periodic testing program that exists at the plant. So every 18 months or 24 months, a plant needs to go into a stop anyway to refuel the plant, to add new fuel elements, in the core. And during that time, this is when you can do some verifications of very important systems. We did that thinking, but it's not something we were the only ones doing it. Some regulators actually also performed their own testing program to obtain independent data, develop independent analysis code, and confirm the behaviors that we're expecting of the passive safety systems. One of the key results of the adoption of passive safety system is the dramatic reduction in footprint for everything we need to ensure the safety of the plant. Not so much because the passive safety systems themselves are more compact, but because they don't require as much in terms of support systems. You know, pumps, as I mentioned before, it comes with ventilation requirements. It often comes with cooling requirements, comes with lubrication requirements. All those are things that add up to the network of systems that you need. In AP1000, because they almost need nothing, we could actually put them all inside containment. And that simplification is something we have applied to every aspect of the plant. We didn't look into simplification just for safety. We looked at simplification for everything. We just love to talk about safety systems that are passive, but it's really something that we had done everywhere. And this led to a dramatic reduction of the safety-related footprint of the plant. And this is an important point because, while it may not be your focus as a young engineering student, but actually this is one of the major drivers for cost of a nuclear power plant, going back to my initial discussion about why we went different. You only have one reactor pressure vessel in a power plant, but you actually have kilometers and kilometers of cables. You have lots of piping to be installed. You have lots of HVAC ducts to be installed. And the more you are reducing your footprint, and the more you are reducing the amount of things you need to install that are extremely high in terms of labor consumption. Modular construction, another way we went different. And again, this is in order to simplify the construction stage, even though it does come with its consequences. But in a modular construction approach, what you're trying to do is bring a number of activities into a factory where you're going to build your modules and then send a prefabricated module to the site where it will be installed. It can be, in order to be transportable, we actually design sub-modules for our largest modules so that it is then assembled on site and then installed, but the principle is the same. Bring as much as you can of the construction activities into a factory environment. In a factory environment, you can obviously, it's easier to work for the worker. You get better quality because it's easier to achieve. And you can also multiply where people are working because you have two people working at your site still on the installation of the modules, the connection, and some of those lower commodities installation. But you also have people working at your module fabrication facility. So you can have more people working at the same time on your project. In turn, this basically allows you to contract the construction schedule by having those parallel working. Of course, one of the significant consequences of modular construction is how early you need to be ready, because you will start the construction of your modules way before it will actually be installed in the plant. So it brings to the left in terms of schedule when you're going to need your design information. We have a number of different types of modules, mechanical modules, which are a number of equipments being mounted on steel frames. But we have very large modules as well, and this is the largest we have, so I took it as an illustration. So it's a civil module, as we call it, so it's structural. It will form the wall of our buildings, but the equipment is also already inside. That module actually is what you see, the opening at the top is actually our spent fuel pool, where we're going to store the spent fuel before it can be discharged from the plant. In the lower elevations, you have all the support systems for the spent fuel pool. But we basically are installing a whole side of our buildings in one go with modular construction. So this module will actually arrive in 77 small pieces to the site, which were prefabricated in a factory. They will be assembled on site, and then we will use a very heavy load crane in order to put it in place. When it's in place, we're actually going to pour concrete, because at the moment, before it's being installed, it's only metallic steel and not yet concrete. But as you can see, the dimensions and the weight we're talking about, again, a big beast. I know that's not very technical as a word, but I think it's aptly describing what it is. And the last topic I wanted to mention in terms of what we did differently is really digital design. Luca already mentioned it, but when we started working on our advanced passive technology, we faced a challenge that obviously we most likely were not the only ones, but there were no good answers in commercially available software. And it was, we had teams working on our design in different places, in Asia, in Europe, in America, and they all needed to work on the same 3D model because they need to communicate about what the plant looks like. And the way we were managing the interface between the different contribution teams was horrendous. So we actually developed in-house how we were going to control all the contributions to the 3D model. And from there came a realization that we were the best ones to know what our needs were, and that we had the capability in-house to develop the tools to accompany our approach to digital design. So through the years, we've added to our suites of software, but all the software that we are developing is always in the same environment. It's always built the same way so that we can easily make them talk to each other, and we can easily add more modules, more functionalities as we identify them. Today, we use that digital design for everything. From cable raceway management systems, actually, deciding where you're going to put your cables and raceways is a huge amount of work. But also just in terms of what the design is, what are the elements of the design, how are we going to build it, there's going to be a significant effort, I think Luca already mentioned it, in terms of sequencing the construction for any future AP1000 through a 4D construction model. But really, this is a tool that we're actually now offering to other people working in this industry because we developed it and it works so well for us. And it's very adaptable, so it is also, we can adapt it to any other people's need. But really, the key message here is that we have this one environment, 3D model environment, that we're using to exchange between designers. We need to have one way which is far from all the paperwork in order to exchange information, to assess any impact from a change in configuration of the plant, and this is what we have achieved with this system. That really allows our engineers to focus on value-adding activities instead of just re-editing drawings just for the sake of a small change. And I think we're going to get back to Luca for some closing remarks before I talk about the internship.
No, I think, just keep going on the internship. I think okay. That's probably the best way of doing the closing remarks. Okay. Go ahead.
So we are calling, for applications to an internship program. So the idea is to be sent 2 months in assignment in our US groups. So it's to be embedded in our engineering groups and work basically as a junior engineer would be, working on the issues or challenges that our customers are facing. It may be something on AP1000, it may be something for the operating fleet, but working with our engineering teams as you would if you were young engineers joining Westinghouse. In terms of the requirements to apply, so to work in the United States, you need a J1 visa. It's not that complicated to get, and we will support all the students to obtain those visas, but obviously it's one requirement is that you don't have anything that would prevent you from obtaining it. You must be a student, so sorry for the professors if you wanted to join, but at this stage we're looking for students. At least 18 years, EU citizens speaking Polish and English. The reason for this is because we are obviously looking at expanding our operations in Poland, so we will be looking for talent soon, and we would like to get to know people who could fit in that office. The 2 months are from mid-July to mid-September. The exact dates are there, so you will be working 40 hours a week. Again, the next requirement about the health insurance, don't worry, we'll help you with it. It's just a small step, but we have to mention it legally. and you can't be a first-year student. We are looking for a little bit more older people. And what we really need you to do, if you are interested, is to submit your CV or resume, as well as your transcript, so the list of your classes and the grades, and a word essay. We said 1,500 words, but it's basically to see how what you're thinking about nuclear power. You submit all this to this link. This link is not findable if you don't have it, but we will provide it to your professors so that they can disseminate to the students. But what is very important is that we need to have people applying before mid-January, and the reason is we need sufficient time to process, well, to select the students and then process the visa before the summer. And that's about what I wanted to say about internships, so I don't know if there are questions or comments. It doesn't look like it. Well, for those of you who are in the room, I'm not disappearing right after we are ending the broadcast, so you can also come and talk to me if you do have questions. And otherwise, we thank you again for welcoming us today. And we hope to see lots of applications from Wrocław Technical University for our internship programs this summer. Okay, thank you. I don't know when they're closing the broadcast.